Now we will discuss about a stress field around a crack tip, how it's look like. Based on this concept, we will discuss a very important parameters of fatigue analysis using what is called using Paris law. They are generally this very important factor which is essential, that related things we generally derive from this stress field around a crack tip concept. Okay. So, let us consider this is a central crack of length 2a and it is subjected to a far field stress sigma, you can say, and it is subjected to, let us consider a biaxial tensile stresses, it is subjected. So, if it is subjected to like this, then in this crack tip, let us consider the axis system is, this is x and this is y axis, okay, at this crack tip. So, at this crack tip zone, just near the crack tip zone, if we take a element at a distance r which makes a angle theta with x axis, you can see. So, in this element, how the, you can say, stress component along, you can say how the stress component along x axis, that is sigma xx, along y axis sigma yy, in this component, how this sigma xx sigma yy and how this sigma xy, that is called shear stress, how it is distributing, that we can find out in terms of radial distance r and this angle theta and the stress sigma. What I am telling, understand? How it is, that things I am going to discuss. So, it is observed that, you see, so I am not going to derive this equation, because if I will go to derive this equation, you can get this derivation from fracture mechanics related topics very easily. So, I am not going to derive this different equation, okay. Where generally you can get, I will provide you the reference book, there you can get this detailed derivation, because otherwise it will take 2 lectures. So, you see, so at a component at a radial distance r and angle theta with x axis, how the sigma xx that you can see in this equation number 1, how the sigma yy is that generally perpendicular to the crack length direction, you can say, that is that stress, how it is, that also we can get, and how this sigma xy means, this is also called tau xy, that is called shear stress component, how it is related with you can say r and theta, and this far field stress sigma alpha, here I have written, that you can easily get. So, from here generally at a crack tip and away from the crack tip with distance from the crack tip, generally how the stress value is varying, that you can say. So, near the crack tip zone, the stress amplitude of sigma y value, here I am showing, is very high. If we go little bit away from the crack tip zone, generally if it is going little bit away from the crack tip zone, then what happens, this sigma yy value which is perpendicular to the crack length, you can say, how this stress amplitude is varying, that I am showing, that is very normal only. Near the crack zone, sigma yy will be the high. If we go away from the crack tip, then what happens, this magnitude of sigma yy also it is reducing. So, these things how it is varying with r, this is generally showing here. Here always you should keep it in mind, this derivation which we have made, this derivation is in terms of, you can say, opening mode stress intensity factor K1. So, K1 is called mode 1 stress intensity factor, this is called mode 1 stress intensity factor. This you should keep it in. This is is a very critical component, you can say, for LEFM. That is why this K1 we will consider in this whole LEFM approach. This you should keep it in mind. Opening mode is the most critical and crack propagation and crack initiation mode. This you should keep it in mind. So, that is why this in terms of K1, how this sigma xx, sigma yy and tau xy is varying, that things here it is showing. What is K1? K1 is called stress intensity factor. This stress intensity factor was generally first found by a researcher whose name is G. R. Wynne. In long back, it is in 1957, who find that stresses around a crack tip in terms of a scaling factor. This scaling factor you can say is called stress intensity factor. How we find out this stress intensity factor? That is generally represented as K1, that I am showing. So, for the analytical solution which we have got, already I have shown, that is sigma xx, sigma yy and tau xy in terms of this K1. So, here once theta equal to 0 in this generally opening mode, theta equal to 0, this opening mode means sigma yy, what will be the sigma yy value? If theta equal to 0, that is along the crack line, because we know this how the crack line, here you can see in this case this is our x, here you can see this is our y. So, along the crack line means along x axis, where theta equal to 0, because generally theta this way generally we make theta. So, where theta equal to generally 0. In this case generally what we observe, we can write the sigma yy in terms of K1 by root over of 2 pi R1, where R1 generally you can say this x we consider as R1. So, here x is that things here I have written, x is written as x is equal to R1 at a distance, generally it is written. So, here this sigma yy can be represented as like this, where this top what it is called top side part, that is sigma 0 square root of pi a, this is called what is called K1, or you can say mode 1 stress intensity factor. So, this is generally along the crack line where theta equal to 0. At that case generally what is K1 value? That K1 is called sigma 0 square root of pi a. So, here always you should keep it in mind, this K1 which is related to sigma 0 means far field stress, means in the sense this you can say this is actually sigma 0, instead of sigma alpha you can write this is sigma 0. Okay. Now, it is observed that what it is called, so along x axis K1 can be represented like this. So, this K1 depends on geometry and you can say boundary condition of the what it is called crack surface, this you should keep it in mind. So, that things also here I am showing, that is why instead of representing K1 is equal to sigma 0 square root of pi a, as it is depends on boundary condition and some modifying geometrical correction factor, that is why one factor y is coming. This y is called geometrical correction factor. This factor y is depends on boundary condition as well as crack type, this you can say. Like I am just showing some example. Then first case you can see, that is why this K1 is represented as K1 is equal to y into sigma 0 square root of pi a, this you should keep it in mind, because it is dependent on some geometrical correction factor y, that is why this y should come into picture. Some of the example I am showing, like you see for this opening mode, this first case you can say let us this figure 1, in this figure 1, S crack is there, which have a half length is A, you can say. If this width of the specimen is much greater than this A, then it is observed that this K1 geometrical factor, correction factor is coming as 1.122. This types of configuration, this Y is coming as 1.122. Whereas, let us consider another example where the central crack is there, the central crack length is 2A. So, in this case, this geometrical correction factor Y, which is a function of, you can say, this Y is a function of A by W. How it is? It is observed that this Y is depends on a square root of cos pi A by W. This you should keep it in mind. So, if A by W ratio vary, then this Y value will vary. This is for central crack types of things, which is subjected to what is called opening mode, far field stress sigma 0, or you can say here sigma 0, here it is considered sigma alpha. So, this you can consider as sigma alpha also, here it is considered as the sigma 0 equal to sigma alpha. This you can, this is also called far field stress, this you should keep it. So, this stress intensity factor is depends on factor that is called geometrical correction factor Y, this you should keep it in mind. Now, we are going to summarize these things. So, first of all, because this stress intensity factor is a very important parameter for LEFM, that is why I am discussing these things little bit in detail. So, what we can write, stress intensity factor generally is a value which is estimating the stress condition around a crack tip. That means, around a crack tip, I have already shown, around a crack tip, this sigma xx, sigma yy, tau xy, which is a function of, you can say, K1. This you should keep it in mind. This equation you can see, because everywhere sigma xx is we represent in terms of K1, sigma yy we represent as in terms of K1, and sigma xy also we represented in terms of K1. That is why you see I have written this stress intensity factor is a value which estimate the stress condition around a crack tip, and it is also the capability of the material for fracture due to an applied load. This stress intensity factor also represent when the fracture of a material is taken place for a particular load. How? Everything in details we will discuss. A stress intensity factor already I have shown that it is represented as y sigma square root of pi a. How its unit is coming, everything in details I will discuss. Its unit is generally MPa square root of meter. What I am telling, understand? This stress intensity factor, its unit is MPa square root of meter, because sigma unit is what it is called MPa and meter is crack length A. Now, what is critical stress intensity factor? Critical stress intensity factor is that factor when the crack length become critical, and at that critical crack length generally the component is not able to sustain the further load and its catastrophic failure is taken place. What I am telling, understand? So, at that critical crack length, whatever the stress intensity factor K1 we got, this critical crack length is a special value of crack length, which generally give us a special value of stress intensity factor, that generally at that stress intensity factor generally the material get fracture. This you should keep it in mind. So, what happens? So, at this critical crack length, whatever the stress intensity factor KIC we got, this has a name, this is called. So, at critical crack length, whatever the critical stress intensity factor we got, that is called fracture toughness. And one thing you should keep it in mind, this critical stress intensity factor is a material property, always you should keep it in mind. This critical intensity factor is not, you can say, it is independent of other factors. So, it is act for a particular material, generally the critical stress intensity factor is, you can say, is a material property. This you should keep it in mind. Now, we will discuss about what is cyclic and threshold stress intensity factor. This is also required in Paris law, that related we will discuss. Now, first of all we will discuss about what is crack growth rate. Crack growth rate means you can say if there is a crack that can grow, then the life of that component is determined this by the crack growth rate. So, crack growth rate is generally, it is not in terms of time, it is generally represented in terms of number of cycle. That means, with number of stress cycle, how the crack length is increasing or propagating, that is generally called as crack growth rate dA by dN, where A is called crack length and N is called number of cycle, number of fatigue cycle, you can say. So, this is generally called as crack growth rate. Now, what is crack growth threshold? So, already I have told you, generally compressive stress which act as a crack closing. So, if there is a compressive stress in a component, then what happens, it is generally try to close the crack. If a body is subjected to let cyclic loading, in this cyclic loading there is some negative stress or positive stress. So, this negative stress can act as a compressive stress which will act as a, you can say, crack closing types of stress. So, that is why to open the crack generally there is required a threshold value of stress intensity. What I am telling, understand? A threshold value of stress intensity, in the sense a threshold value of stress is required. Why stress intensity or stress I am telling? Because we need some stress level, beyond that generally you can say crack can start propagating. Below this crack is not propagating. Why I am telling this stress intensity factor? Because K is a function of stress, because K is equal to, you can say, Y sigma, you can say square root of pi a, correct. So, it is a function of sigma, this you should keep it in stress. That is why this K1 which I am just showing. So, for compressive types of stress, generally this stress intensity factor whatever you will get at that stress level, generally what happens, I have already told you, crack generally at compressive stress it generally close the crack. So, what happens to open the crack, there is generally, that is why required some a stress level, or you can say some stress intensity factor. So, that stress intensity factor range is called threshold stress intensity factor. This you should keep it in mind, because there is a stress intensity K1 that is called, you can say, K1 opening, or in short form you can write K1 opening OP. This, if the stress intensity factor reaches that K1 opening, at that time generally what happens, your crack start propagating. This you should keep it in mind. So, what is stress intensity range or cyclic stress intensity? First of all we should know. After that we will discuss what is threshold stress intensity range. So, you got the idea. You see, let us consider there is a K mean value and this is the K opening stress intensity factor, and this is K max stress intensity factor. So, K mean to K opening, at that point you see there is no growth of crack, that I am showing. So, from here to here no growth of crack is there till this location. After that generally once this crack opening stress intensity factor cross, then what happens? With further increase of stress intensity factor or stress value, you can say the crack start to grow, that I am showing, that is generally called del sigma grow. If this in this del sigma range, this crack will grow or crack will propagate, that you can say. So, you see, so for that generally where no crack growth is taken place, till that location we generally consider a term that is called threshold stress intensity range, that means delta K T H. This is called threshold stress intensity range. This threshold stress intensity range is a limit. Below this crack will not propagate, above this threshold stress intensity factor crack will grow or crack will propagate. This you should keep it in mind. So, to discuss about this threshold stress intensity range del KTH, first of all we should know what is cyclic stress intensity factor, because generally stress intensity factor which we are calculating, it is generally we know K1, it is actually y sigma square root of pi a. Okay. But in case of fatigue, there occur a cyclic types of loading, repetitive types of loading or cyclic types of fluctuating loading. So, that fluctuating loading have a minimum value and a maximum value. That is why there we can get two value of, you can say stress intensity factor. One is called K max, that you can write as y sigma max square root of pi a, this you can write, and there will be a minimum stress intensity factor for a cyclic loading, that is generally y sigma min square root of pi a, correct. So, as in case of fatigue analysis there is a cyclic types of loading, that is why instead of using K max or K min, here we use cyclic stress intensity factor. Cyclic stress intensity factor is the range of, you can say range of stress intensity factor from minimum to maximum. So, that you can represent as del sigma K I is equal to K max minus K min, this you should keep it in mind. So, this is a most important factor in case of what is called Paris law or fatigue life estimation using LEFM, that is why I am representing like this, this you should keep it in mind. So, you got the idea what is del K I. Okay. Now, based on this cyclic stress intensity factor, there is cyclic threshold stress intensity factor. This cyclic threshold stress intensity factor, I am writing SIF, which can be represented as del KTH, which is generally you can write as, in this case you can write as, because where no growth of crack is taken place till the cyclic stress intensity factor range, that can be represented as K opening OP minus K min, this way you can represent. So, apart from this thing, this cyclic stress threshold stress intensity factor we can estimate by using some STM standard, STM standard E647, this you should keep it in mind. This standard describes two methods for threshold cyclic stress intensity factor. These two methods, one method is generally considered testing at a constant stress ratio R. What is stress ratio R? You know, stress ratio R is sigma min by sigma max. this is generally constant. For one cases it is considered as constant and calculate the threshold stress intensity factor range, you can say. Another method is called testing at constant maximum stress intensity. So, another method that is called testing at a constant maximum stress intensity way. Okay. These two methods generally we use according to STM standard E647. By this we can calculate this delta K TH. So, delta K TH is a cyclic stress intensity factor from where generally crack start propagating. This you should keep it in mind. Okay. So, this in detail generally here we have written. So, the threshold here I have written threshold stress intensity factor for a sustained crack growth in this sense that above this value any initiated crack will continue to grow and below it generally growing crack will arrest. This you can say. These are the things you should keep it in mind. Now, we will discuss about what it is called Paris law or Paris-Erdogan law. We can say simply Paris law or you can say Paris-Erdogan law. Okay. Paris law generally applicable in phase 2 or stable propagation zone. This crack propagation, crack initiation and fracture, these things we can represent in case of a log scale. So, this log scale, this y axis or you can say coordinate represent dA by dN and this you can say abscissa represent stress intensity factor range delta K whose unit is MP square root of m meter. This is also in log scale, this I am showing here. So, here just we are roughly showing some value we are putting for a particular types of material we are showing. So, what happens here generally this crack first stage you can see this is from here suddenly crack is not starting. To start crack generally you see some value of delta K is required. So, at that location whatever the delta K we got that is generally called as threshold value of stress intensity factor range. This you should keep it in mind. From there generally crack start to grow. So, what we observe that up to certain level you can see this crack propagation rate is very slow, this you can say. So, low speed propagation you can say, this is called phase 1 or low speed propagation, because here dA by dN is slowly increasing. What I am telling, understand? It is slowly increasing, this you can say. Then the stress second is coming, which is you can say the major portion of the time of crack propagation, this second stage is taken. This is called phase 2 what it is called crack propagation. In this phase 2 crack propagation it generally you can say propagate in log scale in a you can say almost linear manner. So, this is called stable propagation zone. So, in this zone you can say in log scale you can represent this is a linear curve. How it is that also I will show. So, in this stage second zone generally majority of the time of crack propagation is taken place. That is why here generally we can use a power law. That power law is related to rate of change of crack propagation with respect to number of cycle, that is dA by dN, which can be represented as C into delta K to the power m, where C and m are two constant in this stage 2 zone. This is called material constant. This material constant we can find out experimentally, this C and m, and delta K is called stress range, which is generally representing in you can say abscissa or horizontal axis. So, this relationship was proposed by Paris Erdogan's. That is why this is called Paris law. In log scale, generally this dA by dN we can represent in terms of a linear form. That is why here this equation which this portion which I am showing in stress 2, it is a almost linear or a stable propagation zone. What I am telling you, in log scale how it is become a linear, this power law, that I will show. Okay. So, after that this stress 3 is coming. So, where generally this crack propagation rate is very fast, and after that at this cross point x, it generally give us, you can say, critical KIC, critical stress intensity factor, and at that location whatever the crack length we get, that is called critical crack length AC. AC is critical crack length. This you should keep it in mind. Okay. So, where generally catastrophic failure is taken place. So, this middle zone where the major portion of the or major time of the crack propagation is taken place, that zone generally applicable for that in this zone Paris law is applicable. Okay. And this phase 3 which is high speed propagation zone, it takes very less time and suddenly some catastrophic failure is taken place. This you should keep it in mind. Now, this C and M which are called material constant, and C value generally is less than you can say less than 1, you can say always. So, it is varying from 0 to less than 1, whereas you can see this M value generally it is varying from 2 to 4, here it is given, some book it is 2 to 7, what I am telling, understand, like this it is varying, it depends on material types. Generally for non-corrosive environment, this you should keep it in, if it is non-corrosive environment, there generally this M value is within a range of 2 to 4. But if it is a corrosive environment for like salt water, sea water, generally this value is what it is called, can be higher side, it can be up to 7 also, what I am telling, understand. So, in this equation where A is called crack length, N is called number of cycle, and delta K is called cyclic range of stress intensity factor. This curve which I am showing here, this is generally in log scale, always you should keep it in, this is in log scale, that is why it is in linear form. Now, this equation 1, that is Paris equation, if we take log in both side, what it give? You see, it give us log dA by dN is equal to right side, it will be generally log C plus M into log delta K. So, what does it means? It is a equation like in log, let us consider, this is log dA by dN, okay, and this is our log delta K, this x axis is log delta K. So, if we draw a straight line like this, so this intercept generally represent as, you can say, log C, this intercept is log C, and here the slope is, this is 1 and this slope is M, this you can represent like this. So, the equation of these things we know as y is equal to mx plus c, like you see, like this is our y axis and this is our x axis. If from here to here, if let this c, and if it is as m, then this equation we can write as y is equal to mx plus c. So, similar things here also you can see, this log, if we take both side of this equation, if we take both side of log, then what we will get? This side also if we take log, then what we will get? So, this right side we can say log C plus log delta K to the power M. So, this also further you can write as log C plus M into log delta K. Okay. So, in next lecture I will discuss about more details about what is called linear elastic fracture mechanics approach. There also I will solve some problem on this linear elastic fracture mechanic approach. Here M generally always you should keep it in mind, whatever the M you are getting, this M is generally unitless, but this C has a unit. This C unit is generally meter per cycle, which is not a unitless quantity. This you should keep it in mind. Okay. So, next lecture I will start from here. Thank you.